which the most important thing in the physical layer is that we have bits, zeros and ones, and all we care about is how to represent what is a 0 and what is a 1 through the wire in terms of electrical voltage, or through the air in terms of electromagnetic waves, and how to differentiate between the zeros and the ones and submit them through some channel. So basically we have a physical connection and an endless stream of zeros and ones traveling through that connection. And now in the second layer we will try to provide some structure to this endless stream of zeros and ones by creating what's called frames. And these frames will show where a particular data piece begins and where it ends. And the actual data will be in the middle. So in this layer, we want to achieve reliable and efficient communication with whole units of information, which we're calling frames. This is different versus the individual bits that we have in the physical layer. And the goal of this layer is to achieve this efficient, reliable communication with frames between two machines which are adjacent to each other. That means the machines are close enough to each other that we can connect them with a single cable without needing routers, switches, or anything else in between these two machines. So they have a direct connection, they're close to each other. This is the condition for what we're doing in this layer. So in this layer, layer number 2, we will look at algorithms for achieving reliable, efficient communication of all units of information called frames. Between two adjacent machines. Things that we need to consider for this layer is that on the communication channels we have errors. So communication channels are not perfect. There is noise and interference on the channel, whether it's a wire or it's through the air. There are electromagnetic waves that interfere with our signal. So there is noise. So in this layer, we need to deal with transmission errors in some way. We need to find ways to detect the errors, possibly correct the errors. The way we usually do this is with acknowledgements. Other ways to do it is through various error check techniques such as parity bits, which are added to the original data, in this case payload field, before it is sent to the network, and then the receiving machine, once it gets it, will check these parity bits by calculating them in the same way as the sender, and they're supposed to match. If they don't match, then the receiver knows that there's an error, and either it can try to correct the error by calculating what the data was supposed to be, if there is enough redundant information to do that within the parity check, or it will simply say this is garbage, go ahead and resend it. I'm not able to fix this. So the first consideration here is communication channels make errors because there is noise on the channel. Other things to consider is that we have limited or finite data rate at which we can send the data, or our bandwidth is limited. In other words, the communication channels have physical limitations of the amount of data they can send at once. It would have been nice if they would send as much data as we want to at any time. But they have physical limitations that we need to consider when we are designing this connection. So we need to consider the bandwidth and the latency. That's what we get in the exercise. First of all, how many bits we can send in a second? How long does it take for them to get there? All of these three things here would affect the efficiency of the data transfer. So we will try to solve these problems by creating frames, and another problem that we will solve is called flow control, which has to do with fast senders swapping to slow receivers with data. For example, we have a cell phone. Cell phone is a small device. It has limited power because it has a small battery. It has limited processing CPU memory power. It has limited storage, free space on. And then it's connecting to a Google web server, which has got huge data centers with huge servers, and they can process millions of requests at the same time per second. And so the phone is trying to download some movie or something, or large amounts of data from the Google server. And the Google is blasting the data at the poor phone with speed of the light. And the phone is getting all the data, but it cannot handle it that quickly. So it gets swamped So we need to think of a way to tell the Google server to slow it down a little bit until we have enough buffer space in our little device to store what it's sending. In other words, until we process what we have in the buffer and free up the buffer for the next piece of data to arrive. So that's called flow control, and that's also affects the efficiency of the connection. And so that's something that we need to consider, and to solve all of these problems, we create these frames. So the frame contains three parts, what we have on the picture. So the frame has a header, then it has a payload field, this is where the data goes. What is this data? If we have a typical normal network with all the layers in it, this data will be coming from the layer above, because each layer provides service to the layer above. So the data link layer provides service to the layer above it. Which one is that? See what it says here?
Network.
Yeah, it's the network layer which is creating packets. So the data link layer is accepting packet from the layer above, and what it does, it takes the packet and considers the whole, everything that's in the packet, the data. And then it adds its headers, trailers, whatever else it wants to add to it, which contains the frame, beginning and end, and data error check functionalities. So if we have network layer, this will be the packet. Packet which came from, accepted from layer above it. Network layer. And then it has a trailer. So the function of this layer is to provide services to the network layer, to the layer above it. The principal service that it provides is to transfer data from the source machine to the destination machine. We already talked about the physical path and the virtual path in the previous lecture. The virtual path is shown with dots here because the layer 2 data link layer on the sending machine believes that it's talking to data link layer on the receiving machine. Data link layer is an isolated layer entity which is has its own functionality separate from the other layers. So whenever it's doing its processing, it thinks that it's talking to layer 2 on the receiving machine and doesn't care about the layers above it and the layers below it, or what actually is happening. But what actually is happening is this solid line here. This is the physical path of the data. It goes through down from the topmost layer on the sending machine all the way down to the physical layer, and when it's received on the receiving end, it starts going up through all the layers until it reaches the uppermost layer, which is usually the application layer. We said that when we're offering, one of the problems we're trying to solve here is the errors. We're trying to detect errors if there are any errors here. So we are able to provide different services depending on how reliable we want the communication to be. We can just source machine sending independent frames, have the source machine send independent frames to the receiving machine without any acknowledgement, without any error check. We can attempt to detect a loss. In that case, no connections are established, but we send acknowledgements. So the receiver has to acknowledge that it has received the frame. If it doesn't, then we know that something is wrong. It didn't make it. We're trying to detect lost frames. Or we can completely detect all the lost frames and track everything down, and if anything is missing, we resend it and make sure that it makes it there. This is pretty complicated. We don't have to do actually that in this layer, but we can do it if we want to. In that case, we have to establish connections, track the pieces, and acknowledge every single piece. But we could do it if we want to. But typically, that's not what's done these days. So we will just briefly look at some methods for creating frames. The first method that we'll look at is called byte count. Okay, so these headers that we're adding, we say they contain control information. They contain the beginning of the frame and the end of the frame. So in the header, we can use a field in the header to specify the number of bytes that this frame contains. So for example, in the beginning of the frame, we will put 5. 5 is the number of bytes that this frame contains. 1, 2, 3, 4, and including the first one makes 5. So this frame total length is 5 bytes. The next one the same. 1, 2, 3, 4, 5. So it contains 5 bytes. The next frame has 8. So we specify the number of bytes in the beginning. Now, errors can happen. We said, there is no perfect channel. There can happen errors, or there can be noise or interference in the channel. If that happens, do you see any problems with this framing algorithm then? The number of bytes is specified in the beginning of the frame. So the receiver gets this sequence of bytes, and the first byte says 5, so it counts 5 bytes, and it knows this is the first frame. So it cuts that off and says frame number 1. Next, frame 2, another 5 bytes, cuts that off here. Frame number 2 is being read. Next. So if there's an error anywhere in the data, it's okay. But if there's an error in the beginning, in the header where it shows the number of bytes, and there was noise on the channel, and that is now showing on an incorrect number. This frame is supposed to be 5 bytes, but it's showing 7. So now the receiver doesn't know that, and there's an error, so it's going to count 7. 1, 2, 3, 4, 5, 6, 7, and we'll cut it off here. And if that happens, then it's going to lose the whole order of all the frames that follow. So it's like a total loss, because it's going to lose everything that follows. So we don't want that. This particular method is called byte count. So in an attempt to resolve this problem, and the way we look at those is because that's how originally the frames evolved. That was the first designer's thoughts on that. Then they saw this problem and they started designing other methods. These methods, we would stuff particular byte sequences, which are called in the sense escape characters, to show that for example, there's a flag in the middle of the data. That's like the flag showing the beginning of the frame and the end of the frame. But this kind of flag can happen in the middle of the data. So we want to avoid the previous problem, we want to have a flag in the beginning of the frame and in the end of the frame, so that if an error happens that destroys the beginning of the frame, it's okay because we know where the end is at least, and we can cut it off, and the rest of the frames that follow will be fine. We're not going to lose our order totally like we did in the first problem. So in this case, we have a special sequence in both in the beginning and in the end, which will tell us where the frame begins and ends. But the problem that we have here is that this sequence can happen in the data. For example, the sequence would be 0111110. This is our flag. Our frame begins like this and it ends like this. But is it possible that this particular sequence of bits can occur in the middle of a photo or video or text file?
Yeah.
It can occur in the middle of a text file. So it's possible. If that happens, then we have another problem. And to resolve this problem, we stuff this special bytes called escape characters, in a sense, in front of the flag to show that this flag is in the data, and It just randomly happens in the data, and it's not an actual beginning or end of the frame. So anyway, the sender has to encode the data in this way, has to scan the data, look for the flags. Once it finds them, insert this escape in the prompt. And the receiver, again, scans it and removes the escapes to obtain the original data. So this method